Hi everybody, we get ready to get started with Jagadeesh's talk, real-time fulfillment planning.
Hi, I'm Jagdish and I'm going to talk about real-time fulfillment planning. So what is real-time fulfillment planning? So Flipkart stores and sells millions of items through its warehouses and seller locations. These items need to be picked from our warehouses and from seller locations, and they need to be delivered to the end customers. So a real-time fulfillment planner is responsible for deciding the schedule, sequence, and the route for each of these shipments from warehouses and from the seller locations to the customers, right? So what exactly happens after a customer places an order? So once after a customer places an order, the item needs to be first picked from the warehouse. It needs to be packed. After packing, the items need to be segregated. So they need to be segregated because they have to be transported to certain locations, and you have different trucks or flights taking off to those particular locations. So if you're in a particular location, say Bangalore, you're going to have to segregate shipments meant from Bangalore differently from shipments meant for Kolkata. So after that, you have transport, and the transport could be multi-hop. So in the sense that the shipment does not go directly from Bangalore to Kolkata, it takes a particular route. So it probably goes to Mumbai first, and then Delhi, and then to Kolkata, right? It takes a multi-hop transport, wherein at every hop you might again have to merge shipments coming from different places and segregate them. So after that, it reaches a particular delivery center in the destination location. Again, it's segregated, and then a field executive takes those shipments, goes to customers' homes to deliver the shipments. So what are the decisions that we need to make during this entire process, right? Which warehouse do we ship the particular item from? Then in what orders the item should be picked, right? When should we start picking for a particular item? Which then, once it is picked, should we just let the other operations flow through, as in first come order, or should we take decisions on holding a particular item at certain point in the supply chain so that other items can flow through? They may be having higher priority, right? Then which transport connection should be taken? Which mode should be taken? Should we take surface? Should we take express surface? Surface is road. Then should we take a flight? Right? Which connection, which mode should we take? So the point is, do we really need to make all these decisions? Are we overcomplicating things? Or can we just let all these operations happen in the first come, first serve order of receiving the orders? Right? And will that serve the purpose? So let's take certain examples. Let's take this example wherein we have a Bangalore fulfillment center, a sort center in Bangalore, and we have delivery centers in Delhi, Hyderabad, and Chennai. So we have transportation connections from Bangalore sort center to Delhi delivery center at 10 p.m. and to Hyderabad and Chennai, we have transport connections at 2 p.m. So let's assume right now it's 12 p.m. and we have received shipments meant for Delhi, right? And we start processing only these shipments meant for Delhi. Let's say by 2 p.m. we have them picked, packed, and sorted, and we have created the bags, and we are ready to load them onto the trucks. At 2 p.m., we do not have any transport connection meant for Delhi. We have transport connection meant for Hyderabad and Chennai. So now what happens? The trucks meant for Hyderabad and Chennai will have to return empty because we never processed anything meant for Hyderabad or Chennai. And as a side effect of that, the sort center is now choked because we have processed, and we have, after processing, we have kept those items at the docking area. If we process any more, we don't have any place to keep them. And we can make place to keep them only after these are now loaded onto a truck. And the truck now comes at 10 p.m. meant for Delhi. So until 10 p.m. for 8 hours, this center is now choked. It can't process anything further. So in this example, we can see how we could have taken a better decision on processing shipments meant for Hyderabad and Chennai at 12 p.m. and shipments meant for Delhi after 2 p.m. That would have been a better choice. This is another example where I'm trying to tell how downstream capacity also impacts the planning decisions, right? In this case, we have a Bangalore fulfillment center, we have a Bangalore sort center, and we have delivery centers in HSR, Koramangala and Banchankri. So first thing which is very uh, which you can see here is that Bangalore fulfillment center has a capacity of 1000, the sort center has a capacity of 900. So definitely you cannot process in Bangalore fulfillment center 1000 per hour and send 1000 per hour to the sort center. It will choke it. You have to send the remaining 100 to probably to some other sort center, right? Now, after they are sorted, we have to take decisions on how many we should process for HSR, Koramangala and Banchankri. In this case, for simplicity, all the transportation are at the same time at 2 p.m. Right? If we consider that we take an arbitrary decision that we are going to sort equally for these destinations, what happens? So Bangalore sort center gets 900 units per hour, shipments per hour. If we have taken the demand load pattern such that 300 were meant for HSR, 300 were meant for Koramangala and 300 meant for Banchankri, what happens is that at this point in time, HSR delivery center has a capacity of 600. Maybe it didn't get load from some other location, right? So this is kind of underutilized. And in this case, Banchankri delivery center at this point in time has a capacity of 200 per hour. Maybe it has got load from some other sort center. So in this case, if we send 300 to the Banchankri delivery center, we end up choking Banchankri delivery center. In the third case, Koramangala does have a capacity of 300 per hour, but the transportation as such, we have capacity of only 200. So we end up choking the transportation here. So the point is, you cannot take arbitrary decisions. You have to take decisions based on the transportation time and the downstream capacity. In this case, a better decision that we could have taken is to ensure that the ratios of the demand that we serve is along the ratio of the transportation capacity and the delivery center capacity, right? So in this example, it's pretty easy and intuitive to take a decision. But in the real world, the Banchankri delivery center or HSR delivery center will not be getting load only from the Bangalore sort center. It will be getting load from a large number of sort centers, right, placed all over India. Next, we consider storage usage. Here we have an example wherein we have two operations, operation 1 and operation 2, and we have storage in between. Operation 1 and 2 both have a capacity of 100 units per hour. They can both process 100 units worth of shipments per hour. However, the rate at which they consume capacity is different, right? So in operation 1, a small shipment consumes 1 unit of capacity, but the large unit consumes 2 units of capacity, which essentially means that here, if all are small, I can process more shipments per hour, right? In operation 2, it's exactly the reverse. Small consumes 2 units of capacity, whereas large consumes 1 unit of capacity. So if you do not use storage well, sorry, at max we can process 50 units, 50 shipments per hour, right? Because even if operation 1 processes 100 units, 100 shipments, operation 2 can only process 50 because small here consumes 2 units of capacity, right? Now, how can we use storage and get a better throughput? So let's take one example wherein in R1, operation 1 processes 75 small units, and operation 2, in this case, can only process 50 small units, but the remaining 25 units can remain in storage. In R2, operation 1 can now process 50 large units, and operation 2 can process 50 of these large units plus 25 which were in storage. So you can indicate to operation 2 to not only process the large units, but plus pick the small units which were in storage and start processing them. With this, we can have an average processing of 62 units per hour, right, versus 50 earlier. This is another example to indicate how transportation batching and routing affects the capacity that we have. In this example, we have a very small network. We have Bangalore, Chennai, Mumbai, and Delhi, right? So if we take the direct route from Bangalore to Delhi, it costs you 100 rupees per shipment. Uh, Bangalore to Mumbai costs 60 rupees per shipment. Mumbai to Delhi costs 60 rupees per shipment. Bangalore to Chennai costs 40 rupees per shipment, and Chennai to Delhi costs 80 rupees per shipment, right? So in this case, the other alternate routes have a cost of 120 rupees per shipment between Bangalore and Delhi, whether I go from Mumbai or whether I go from Chennai. But the direct route costs me 100 rupees per shipment. But the point here is, you never pay on a per shipment basis. You're paying for the truck, right? You're paying for the rental for the truck for one particular route. So it will cost us 100 rupees per shipment between Bangalore and Delhi only if we have a full truckload, right? In this example, let's say one truckload is 1000 shipments. Now let's look at a demand pattern that we have. I have only 500 shipments from Bangalore to Delhi. So in this case, if we decide to take the direct route between Bangalore and Delhi, it's going to cost us 200 rupees per shipment and not 100 rupees per shipment because we don't have a full truckload. So what can be a better decision here, right? The better decision here is you look at the other demand pattern. So we have 500 units from Bangalore to Mumbai and 500 units from Mumbai to Delhi. So you can piggyback the Bangalore to Delhi load by sending it to Mumbai and then from Mumbai to Delhi. You could do the same between Bangalore and Delhi via Chennai as well, because I also have 500 units, 500 shipments of demand from Bangalore to Chennai and 500 units from Chennai to Delhi. Now you have to look at where additional capacity is available for additional processing at Mumbai or Chennai, because you are going to send shipments to Mumbai. They might have to be sorted again for Delhi, right? So in this case, Chennai is the only place where I have additional capacity. So the decision is to send the shipments via Chennai. So this is all assuming that you can still meet the promise or the SLA given to the customer. Let's take another example wherein how priority of the shipments and the breach cost of the shipment and capacity consumption affects the decisions that we take, right? So first thing is, not every shipment consumes the same amount of capacity in your supply chain. So very good example is in the last mile, if the address type is of type commercial versus residential, the field executive can deliver more shipments per hour. In a commercial address type, there are a lot of people at the same place. So definitely the field executive can deliver more shipments in a shorter period of time versus residential like areas like HSR layout or Banchankri, where there are a lot of houses. So to cover the same 100 number of shipments, an FE will take more time in Banchankri residential area versus, let's say, Cessna Business Park, right? Because there are a lot of people who are there in the same location. So in this example, we have supply of 2 units, demand of, we have 4 shipments, 2 of type cash on delivery and 2 of type prepaid. In this case, prepaid shipments consume less capacity to deliver, because a field executive can deliver more prepaid shipments per hour, because in case of cash on delivery, he has to get the cash from the customer, then give back the change. If it does not have change, he has to somehow arrange for it and so on. So on an average, if the shipments are of type prepaid, we can deliver more shipments per hour. So the consumption here is COD consumes 2 units of capacity, whereas prepaid consumes 1 unit of capacity. In this case, the breach cost are the same in both the cases. If we breach a regular shipment, it's going to cost us 20 rupees. If we breach a NDD shipment, it's going to cost us 70 rupees. The only difference in these 2 cases are the service type. In case 1, all shipments are of type regular. In case 2, the COD shipments are NDD shipments, which is next day delivery, and prepaid are regular shipments. So if we look at this, since I have only 2 units of supply, I can either fulfill 1 COD shipment or 2 prepaid shipments. In case 1, if we fulfill 1 prepaid shipment, we are going to breach on 3 regular shipments, so the breach cost would be 60 rupees. If we fulfill 2 prepaid, the we are going to breach on two regular shipments, and the breach cost would be 40 rupees. So the optimal answer would be to decide to fulfill two prepaid shipments. However, in case 2, the same answer is not the right answer, because in this case the COD shipments are NDD shipments. So if we decide to fulfill the two prepaid shipments, the breach cost would be, you are breaching two COD shipments which are NDD, which is 140 rupees, right? So the breach cost is 140. However, if you fulfill one COD shipment, the breach cost is now 70 plus 20 into 2, which is 110, right? So it is more profitable in this case to fulfill one COD. Next important point is the attributes of the shipment or of the supply chain which affect capacity are not the same across every operation. So we discussed an example wherein address type or payment type affect supply chain capacity in the last mile. But in a warehouse, it really doesn't matter whether the address type is prepaid or COD, or whether the payment type, address type is residential or commercial, or the payment type is prepaid or COD. What matters in a warehouse is how far it is from the packing station, because there is some person who is going to go walk around the warehouse, right, picking for certain items and then get them to the packing station, right? So it really matters how far it is from the packing station, or it may also matter on what is the size of the shipment, right? So if there are a lot of mobile phones, he can fit them in his basket, right? But he can fit more things in his basket. However, if they are all larger items, lesser number of things can fit in the basket. So he has to make more trips. So similarly, in a sortation center, the size is again an important aspect. It's a conveyor belt. So if the shipments have more length, definitely less number of items can be sorted per hour versus mobile phones. So all these attributes affect supply chain capacity, and different attributes affect the supply chain capacity differently in different operations, right? The next thing is breach cost or profit, right? They are also impacted by the service type and customer. We have already seen how a regular shipment may not have the same priority as a next day delivery shipment, right? Similarly, a customer type. Let's assume two sets of customers, right? There's one set of one customer who buys from us very regularly, and he stays in Bangalore, where he's used to a better customer experience, right? And let's say we have given him 2 to 4 day delivery timeline, right? And let's say there's a customer in Assam where he does not have much of a choice to buy locally, right? And we have given him 6 to 8 day delivery timeline, and let's say he buys from us once a year. So if you have to decide whether to deliver on the 3rd day to the customer in Bangalore or on the 7th day to the customer in Assam, right? And you have to decide. You have only 1 unit of capacity. It might be a better choice to decide on delivering to the customer in Bangalore, because he's used to much better customer experience and he has a much better choice here. If not you, he might go and buy from some other local store. But that option may not be available in Assam, right? So you might want to take a choice on utilizing this last 1 unit of capacity to fulfill for the customer in Bangalore versus some customer in Assam. So the examples that we have taken, we had very small graphs. In reality, the graph is huge. It's the whole supply chain network for the entire country, right? Now, all the items have different dimensions, different volume, different weight. These result in different shipment costs, and in a lot of cases, different restrictions as well. For example, any product which has a battery is considered dangerous, so it cannot be shipped by flight. It can only be shipped by road. So we have all these constraints. So we have transportation connection time constraints, right? So if you have a truck leaving at 2 p.m., it can at most probably wait till 2:30. It won't wait beyond that. So if you have not processed items meant for that particular destination by that time, then the truck goes. After that, if you process, you cannot say, I have come 15 minutes late, so you can still take some shipments. That's not possible. It's a timed event. Similar thing with a flight. So you have hard constraints on those connection times. And then you have given a particular promise to a customer that you're going to deliver to the customer at some time or some date, right? So you have to ensure that you meet the promise given to the customer, considering all these constraints and at lowest possible cost. So that's the problem statement for us to solve in fulfillment planning. What adds to this problem statement, in addition to the fact that it's a gigantic graph, is the fact that there's high amount of variability, right? It's very, we have seen how location, payment type, address type, size of the shipment, whether it is dangerous or not, affect your supply chain capacity. So it's very difficult to predict how many shipments I'm going to get in this, let's say 1 hour, which I'm going to source from my Bangalore warehouse, and the customer will be in Assam or Delhi, and whether the size of the shipment will be small, payment type is COD, and address type is commercial, right? It's very difficult to predict that. At most, you can predict how many orders you're going to receive every day. It's very difficult to predict at this granularity on number of shipments you're going to receive. So there's huge amount of variability on the destination mix, product mix, the seller mix, and service mix, right? So all this variability adds on to your complexity of the problem. Next, we have supply variability. A large amount of the workforce is temporary in nature. The transportation capacity is unreliable, right? So your supply side also, you have lot of variability. You have to match this demand variability with the supply variability and then fulfill with the constraints at the lowest possible cost. Now going on to solutioning, the first thing that you need to do is to model your problem statement, right? So you need to understand what are the various operations that happen in your supply chain. So the first thing is to understand the kind of storage that we have. So storage can be planned, unplanned, or semi-planned in nature. So in a planned storage, you can keep a particular item at a particular location, right? And when you want to process it, you can say, okay, fetch me this particular item. You exactly know where it is. You can go to that point and fetch it. So a warehouse is that kind of a storage. It's a planned storage. Next, you might have semi-planned storages, wherein you can have areas separating. You can have areas wherein you can say this area is meant for Bangalore shipment, this area is meant for Mumbai shipments. So you can say, get me any 100 shipments meant for Mumbai, or get me any 100 shipments meant for Delhi. You can't say exactly which shipments, but at least on certain attributes you can say, get me this shipment. So that's kind of a semi-planned storage. Then you have completely unplanned storages, wherein there are just shipments there. You can process any number of them. You cannot define what kind of shipments you want to process. Next is operations, right? There are a lot of operations that are going on. So as we discussed, we have pick, pack, sort, bag, transport, and so on. Now, which of them do you really want to understand when you want to plan, when you want to create this global plan? The more operations you understand, your plan would probably be more optimal, but it might get very complicated. Your problem statement might now get very complicated. Plus, at very low granularity, it may be very difficult for operations to tell you what is their capacity. For example, pick itself may be many operations. Pick and pack themselves may be many operations. So probably he first creates a pick list. He goes and the field executive goes and walks. He scans whether this is the right shipment, puts it in the bag, then takes it to some place. There they generate some invoice, tick that invoice. So how much of it do you really want to understand? Because more you try and understand, it's very difficult for someone to tell, how many pick lists I can generate, or how many labels I can print. But somebody can definitely tell, all this combined, I can do 100 units per hour, right? And the more the more granular operations you try and understand, your graph becomes bigger and bigger. So you need to take a call on at what granularity you wish to understand. Next thing is modeling capacity. So you need to model capacity by understanding how the attributes of the shipment and the kind of supply chain that you have affects your capacity. So some of the examples we have already discussed today, right? Next thing that you need to understand is lead time. So lead time is the time difference between you placing a request versus that request getting served, right? For example, let's assume there's a coffee machine. It can make uh, one coffee for every minute, right? So it can make 60 coffees in 1 hour. So the capacity of the coffee machine is 60 coffees per hour, but the lead time is 1 minute. So you have to wait for a minimum 1 minute in order for the coffee to be served to you. Let's assume that the coffee machine has a different kind of design wherein it makes coffees in bulk, right? So it makes 10 coffees at one time. So it still takes 10 minutes to make 10 coffees. So your capacity is now same 60 per hour, but your lead time is now 10 minutes. Because it's making coffees in bulk, you have to wait for 10 minutes to be served one coffee. Another thing that affects your lead time is the queuing. Assume there are 30 people waiting for the coffee at once. So for the first 10 people, the lead time is 10 minutes. But for the next 10 people, the lead time is 20 minutes because 10 minutes they have waited in the queue and 10 minutes is the processing time. So taking this step further, so what we do is we model every time slot in which any operation can happen as a vertex in a graph, as a node in a graph. So in this example, we have a fulfillment center 1 in which there are 3 tasks being performed. You can assume they are pick, pack, and maybe sort, right? The slot represents a 1 hour slot. So each of this is a node in the graph, and the edge represents the flow of your demand from one node to the other node. So in this example, the slots have a capacity of 100 units and the lead time is 15 minutes. So in this case, although this slot 1 can process 100 units in the first hour, only 75 can flow to task 2 in the first hour, because the items processed in the last 15 minutes will flow to slot 2. So the edge represents the flow of your demand. Now how do we create the plan? The first step obviously for you is to consider the whole supply chain network, the various tasks and operations which take place, and the slots in which these operations can be performed, and create the graph. Next, based on the demand that we have received, we have to identify the start and terminal nodes. So if the shipment is going to be fulfilled from a warehouse, that's your start node. And the customer locations or the delivery hub becomes your terminal node. The first point for us to consider is what is feasible in every slot in a delivery hub, right? You are going to pick a plan only from what is feasible. So that checking your feasibility helps you reduce the data set from which you have to pick your plan. So the feasibility is equivalent to you trying to find the shortest path from your fulfillment center to a particular slot in a delivery center and see what is the fastest you can reach. You can assume you don't consider capacity or any other demand pattern. You just see, let's say this is the highest priority shipment. When can I reach the delivery center at the earliest? So that from that point onwards, it is feasible in the delivery center. Prior to that, there is no point even considering this in your plan, because no matter what you do, it can never reach the delivery center prior to that. So that becomes your feasible set. Now next you have to decide what do you want to optimize on. Now you have a feasible set, you want to now decide among this feasible set, considering the capacity that I have and the constraints, what am I going to fulfill? So that's your optimization function. A simple optimization function could be, I want to maximize my profit. And profit could be, what is the profit I earn on every shipment? minus how much do I pay if I breach this shipment, and how much you paid when you breach this shipment would be, let's say, what is the probability of breach if I don't process in this slot, what is the probability that I'm going to breach this shipment, into how much am I going to pay if I actually breach this, right? So that's your optimization function. So based on your optimization function, you start deciding from the delivery center, which are your terminal nodes, what allocation you want to do. So you have certain amount of capacity, what do you want to fulfill? So you take certain allocation decisions, you pass on those decisions to the previous nodes, right? When the decision comes here, again there are multiple decisions coming from various nodes. You take the decision at this node based on the aggregate demand coming from this node and this node, right? So you take certain decisions and you go on until you reach your source node. By the time you reach your source node, see, at any point if you have enough capacity, there is no decision to be taken. Only when you don't have capacity, you have to decide what not to do. So you keep taking decisions on what not to do. So when you reach here, you know whatever decision you have taken is feasible end to end, right? It may not be an optimal decision. So this cycle is called a backward propagation flow. Now you do a forward propagation flow. In the forward propagation flow, you try to learn on what are some of the suboptimal decisions you have taken, right? And in the next backward propagation flow, you try to correct those suboptimal decisions by taking a better allocation decision now. So this you continue this process. You continue this process across various flows. At some point in time, your decisions will converge, in the sense that there will be one forward propagation cycle wherein you have neither allocated anything new nor have you learnt anything, which means that there is no scope for further improvement. So that becomes your plan. You can also take a time cut to the plan. I'll come to that later on, why you might have to take a time cut to the plan. So this is at a high level on how the algorithm starts taking decisions, right? I have not gone deeper into the algorithm, but the point now is, how do you scale this? Because you have large number of nodes, right? You have hundreds and thousands of nodes and millions of edges. How do you scale this algorithm? So that's where BSP and Pregel come into the picture. So Pregel is a paper by Google which covers how you can parallelize graph algorithms. So at a high level, the point is you break down your graph into sets of vertices. You have you distribute these vertices across various machines. So now you can process in parallel, and you model your algorithm as some computation which happens at a vertex plus message passing across vertices. So each vertex does certain computation, and then it passes on its decision to the next vertex as a message. And that's how you scale or parallelize this algorithm. Let's take certain examples. This is a very simple example wherein I have 4 nodes, Mark, John, Anna and Clara. Each of them have an ID. So Mark has an ID of 32, John has an ID of 41, Anna has an ID of 18, Clara has an ID of 62. And the problem statement is, find out the largest ID in this network. If you are running this on one machine, the algorithm would be you kind of do any kind of traversal and you keep track of the largest ID seen so far. But let's assume you cannot run this on one machine. Then how are you going to parallelize this algorithm, right? So the way you could model the algorithm is, each vertex gets certain messages. It looks at those messages and sees what is the largest ID that I have, right? If the messages that it has received contains ID larger than the ID it has seen so far, it updates it and then sends out a message to its neighbor saying that I have seen a larger ID now, right? So in this case, in the first step, so John sends a message of 41 to Mark and Anna. Anna sends a message of 18 to John and Clara. Clara sends a message saying 62 to Anna. Mark sends a message to John, right? So in this case, John gets a message of 18 from Anna and 32 from Mark. So he compares and sees, this vertex compares and sees, okay, I don't have any larger ID which I have seen, right? The ID which I had seen earlier is the largest. So nothing happens. But Mark sees that I have got a message which is 41, which is larger, updates and now sends a message again. So in this case, Anna gets a message of 62, right? Anna updates its own IDS or the largest ID seen so far as 62 and sends a message, right? Over two more steps, the algorithm converges wherein everyone now has an ID of 62 and no further processing happens. So this is when your algorithm converges and you have actually now processed the algorithm in parallel over various machines. So I'm kind of short of time, so I'm going to skip the next example of shortest path of how you can model shortest path as a distributed algorithm, right? So next, going on to how we have actually implemented it. So Pregel is a paper, right? Giraffe is an implementation of Pregel, which is open sourced by Facebook. So the fundamentals are the same. So you have inbox, you have outbox, and the graph is divided among a smaller group of vertices. Each group of vertices are given to one worker for processing. The worker has multiple threads. So what happens is the threads take message meant for a particular vertex, give it to the vertex, some part of the algorithm runs as part of the vertex, you get a message now, and that goes to your outbox. And then this message is taken from this outbox and delivered to the next vertex via netty. Here, the problem is what happens if a machine crashes, right? You have some set of workers which are running on this machine. What happens if they crash? That is where Giraffe uses yarn. Yarn is used for high availability. So whenever a worker crashes, the worker now comes up on another machine. So each worker is modeled as a map task which runs infinitely. And the communication across vertices happens over netty, and Zookeeper is used as a distributed coordinator here. So Zookeeper keeps track of which worker is on which machine and which vertices are mapped to which worker. And any change when a machine crashes, the coordination happens over Zookeeper. So mapping this to our algorithm, again the vertices are nothing but time slots in a facility or transport. The edges are movement of shipments across these time slots. Messages are the allocation groups or the learnings that we have in every cycle. And output is a set of plan, right? So do you always get an optimal plan? No. So in this example, the y-axis represents the goodness of the solution and the x-axis represents the solution set. So let's say we started off with some solution here. The way the algorithm works is it tries to learn something and comes up with a better allocation. So with better allocation, it may reach here, here and so on. And when it reaches here, any neighboring decision is suboptimal, right? So you have got an optima, but it may not be the global optima. There might be a much better a plan. So at this point in time, what you might have to do is take a set of random decisions so that you land up somewhere here. And when you run this algorithm again, you can get to the global optima. But another key point to consider is that there's also a time aspect of this algorithm. If you run the algorithm for 24 hours and you get the best optimal answer, it's useless. Because finally you have to tell the warehouses and the facilities what they need to process. And the more time you take, the more the demand and supply pattern changes, so your answer may be outdated. So you have to consider the time angle to this particular run as well. So what we do in production is we keep a time aspect of it. If we can converge before that time, it is fine. Otherwise, we stop it at that time and send out whatever plan we have seen so far. So after you complete your global plan, there are still a lot of decisions that you can take locally, right, without affecting the global plan. For example, once your shipments reach your delivery center, in what order the FEs should go and deliver the shipment so that petrol cost is minimized. That's another decision, right? So that's a local planning, last mile vehicle routing problem decision that we take. And that's done independently of your global problem. So after your global plan is created, there are some other local plans which you need to create with the constraints that the global plan has given. Yes, so that kind of completes what fulfillment planning is.
We have time for 2 questions only.
Yeah.
Hello. Yeah. It's a two-part question. Uh, on a high level, you mentioned that if there is a customer A from Bangalore who's a repeat purchase customer and a customer B from, let's say, Assam, I do understand that from the variables you've considered, customer B makes more sense. But keeping in mind, specifically here, the way Flipkart's growing across its competitors, the amount of money or capital invested from a branding perspective, you're also looking at getting new customers. Assuming I'm a loyal customer of Flipkart, a 1 day delivery in so many purchases I make might not really affect me. But getting new customers onboarded for their first initial purchase is primarily more important. Are you just looking at it from a high level perspective right now, or are you actually taking these core, from a brand perspective, variables also into your delivery?
Okay, so this is an example, right? So for the algorithm, everything is a constraint. So this is a business decision to be taken. Right. Which customer is more important is a business decision. It's independent of the algorithm. This is just an example to say that, let's say if I have to breach, I have to take a decision on what to breach. And what to breach is also an aspect of the customer. So the large number of constraints. One of the constraints is who is your customer as well. This is an example wherein today I want to take a decision that I want to serve my repeat customers better than a customer, say, who buys from me once a year. But business could come back and say that the customer who buys from you once a year is a customer whom you want to give more importance to. So the algorithm is independent of that.
The second part of the question would be, whenever we go to the checkout page, there's a delivery estimate. Right now, is the delivery, as I see, it's extremely granular and it's not very specific, but you try to live up to the delivery date. The estimate delivery dates, are they based on historical data or some kind of initial query itself where you have an idea?
So currently, what you say is an estimate is what we call as a promise. So that's based on some aggregate planning that we do, right? Some kind of a bulk planning. We consider what demand we might get, some prediction on how much demand we will get, how much will be our supply. Based on that, we come up with the promise. Now, the better way to improve that promise is to have a feedback loop from this planning, which feeds back to the promise, so that we can improve our promise, right? So that's right now not implemented. So that will help us improve our promise.
Thank you, Jagdeesh. We have to stop, guys. The other talk is over, so the crowd is headed over here for the next talk. Thank you so much.